talk is on, in my opinion, a very interesting and fun project that's the problem of differential private multi-sampling, and the talk is going to be given by Devin Schneider.
Thanks for the introduction. So yeah, I'll be talking about differentially private multi-sampling from distributions. Okay, so what is this problem? At a high level, we have been given some input samples from some distribution P, and your goal is to come up with an algorithm that generates outputs M samples from some other distribution Q. And you have two goals: accuracy, you want Q to be close to P, and privacy, the algorithm should satisfy differential privacy. So this problem has been studied a little bit before for the case of M equal to 1, where you have to just generate one sample. This is called private single sampling. And in this work, basically what we do is we try to study the sample complexity of private multi-sampling. And the question is, can we do better than M times the sample complexity of single sampling? In a sense, like if you have a single sampling algorithm, you can run it M times, and then the sample complexity will scale linearly with M. Can we do better? Okay, so first I'm going to give you an overview of what is differential privacy, because maybe a lot of people in the audience maybe not as well aware like what it is. Then I'll talk about prior work. Then I'll define what is private multi-sampling and give some baseline techniques to achieve it. And finally, I'll give you new private single and multi-sampling algorithms for the distributions over 1 through K. Okay, so what is differential privacy? You should think of it as being a property of an algorithm. So an algorithm is differentially private if it sort of does not reveal if a particular person was present in the data set. So you have these two data sets, X and X prime, where only the third person is different. And looking at the output of an algorithm, it should be difficult for an adversary to figure out, hey, was it X or was it X prime? More formally, an algorithm is epsilon differentially private if it satisfies this kind of inequality. Note that the two probability terms here are related by this multiplicative factor of e to the epsilon, and this epsilon is the parameter which helps us to quantify the amount of information leakage. And you should think about smaller the epsilon, more privacy that you have. Okay, so now let's move on to private single sampling. Well, why should we study it? Well, a simple motivation is just exploratory data analysis. I'm still not sure what I want to do with the data. I just want some representative samples from a distribution while making sure that I ensure privacy of the individuals. So this was first studied by Rashwadnikova et al. So as an input, you have been given n independent samples from some distribution, from some specified class C, and your goal is to privately generate one sample from a distribution Q, which is somehow close to P. And note that the randomness of the output that we're considering here includes both the randomness of the input X as well as the internal coins of the algorithm. And our accuracy notion here is total variation distance. We want P and Q to be alpha close. So there has been some prior work on this, primarily on the sample complexity of this task. So Rashwadnikova et al. Looked at distributions over 1 through K and product distributions over the Boolean hypercube. Then Ghazi et al. Looked at d-dimensional Gaussian distributions. So now, what are our contributions? So we come up with new private single sampling algorithms. We define what is private multi-sampling and come up with two notions, strong and weak. We come up with new private multi-sampling algorithms, and finally also some lower bound techniques. Okay, so what is private multi-sampling? It's the same problem as before, but now only you have to generate m independent samples from the distribution Q instead of just one. And now there are two accuracy notions here, weak multi-sampling and strong multi-sampling. In weak, what we are asking for is like each output sample should be individually close in total variation distance to P. So you just want the distance between P and Q to be small. Whereas in strong multi-sampling, we want that the output samples are somehow jointly close to P. And therefore, we want this P cross M and Q cross M to be alpha close in total variation distance. And now let's go over some baseline techniques. If you have a single sampling algorithm, you can just repeat it m times on independently drawn data sets, and that gives you a weak multisampler with sample complexity m times the original one. Similarly, if you have a weak multisampling algorithm with just a simple change of parameters of alpha to alpha over m, you get a strong multisampler. So let's focus on distributions over 1 through k. What do we know at this point of time? So single sampling can be done with k over alpha epsilon many samples. And for weak and strong multisampling, you are paying an additional multiplicative factor of m and m square. And we see that at least for weak multisampling, this is scaling linearly with m. And so can we do better? Like somehow the average cost to generate is still the original single sampling thing, right? And we say that yes, we can do better. And I'll now give you a better weak multisampler for distributions over 1 through k. So first I'll give you a private single sampling algorithm, and then I'll modify it to give a weak multisampling algorithm. Okay, so we have n samples. Well, one of the easiest things that you can do is just apply this algorithm called k-array randomized response on it. What is this algorithm? It takes an input x, parameter epsilon 0. It outputs x with probability proportional to e to the epsilon 0, and outputs everything else from the domain 1 through k, which is not x, with probability proportional to 1. And if you set this parameter to be epsilon, then yes, the algorithm is indeed epsilon differentially private. However, there is too much noise in this process, and the error is not reducing with the number of samples. It makes sense because we are just using the first sample. So if we have more samples, let's use them. So what we do is first we select one of these xi's at random, uniformly at random, and then apply k-array randomized response. We can show that if doing this very simple step, and this simple step of subsampling, if we include this in our privacy analysis, we can set the parameter epsilon 0 in a much better fashion and achieve a sample complexity which is k over alpha epsilon, which is actually slightly bit better than what it was there in Rasrodnikova et al. There it was 2k over alpha epsilon. And yes, this algorithm is a subsample randomized response, and it is a valid private single sampling algorithm. Okay, so we did our first goal. Okay, so how do we build a multi-sampler out of it? We'll notice that we are first doing this subsampling step and then this randomized response step. Why not try to sort of switch these two? First apply randomized response on all of them, and then do the subsampling. Now I claim that from an accuracy standpoint, these two algorithms are effectively the same. You're just subsampling something and applying k-array randomized response. But now the question is, if you look at this picture, you should ask yourself, okay, why release only one of them? Why not release m of these zi's? And yes, why not? You should be doing that. But the only question is now, because you're releasing more things, the question is how do you analyze privacy? And I claim that analyzing this algorithm is similar to first shuffling all of these zi's and then choosing the first m out of them. Effectively, you're just choosing m without replacement. And this algorithm can now be analyzed using this technique known as privacy amplification through shuffling by Feldman et al. And this achieves the sample complexity, which is a max of m and another constant. And for epsilon greater than equal to 1, we actually gain by a factor of epsilon, and it is basically m k over alpha epsilon plus another log term there. If you're paying attention, you will ask me, well, what is this delta? Like, I have never introduced this delta anywhere in the talk before. So I did cheat a bit. This is not an epsilon differentially private algorithm. This is an epsilon delta differentially private algorithm. So this privacy amplification through shuffling only gives us an algorithm of this type. And what is this? This is basically a slight relaxation of the epsilon differential privacy that I mentioned earlier in the talk, where you have this additional plus delta term. So it gives you a little bit of slack. Okay, so at this point, so what do we have? Well, for distributions over 1 through k, if you're looking at epsilon differential privacy, yes, we do pay with a multiplicative factor of m and m square. However, if you're willing to go to epsilon delta dp, I think which is very common, then you can save a lot. At least for strong multisampling, you can see that we save by a factor of m. And if you look at weak multisampling, let's look at it in much more detail. Let's look at the sample complexity, and let's think, if m is smaller than that expression on the right, then effectively the cost of generating m samples is very close to the cost of generating one sample. Whereas if m is more than that expression, then the cost of generating m samples is basically m. And so effectively, the average cost to generate a sample is just 1. I personally just find it very cool. So yeah, that's. But yeah, that's all. Thank you. And these are some open questions. If you want to discuss more, please hang around. I'll have my poster somewhere here.
Cool. Any questions for Davidovich?
Yeah. I don't know.
Hi, thanks. Could you clarify for weak multisampling? I guess the definition says the Q that you're sampling, or you said something about like at a sample level you need to be within a certain total variation distance. What about the definition prohibits you from, I guess, just taking one sample and then outputting k copies of it?
Yeah. So as I said, like for weak multisampling, you want independent samples. So if you just take one sample and just produce k copies of it, so that will not work, and that's why we have that independence also, like inside the definition of what it means to weak multisample.
Okay,
And even for strong multisampling, actually, if you do that and just copy them, it will be similarly close. And so that's the question, and that's the third point. Like, are there alternative ways to define while we remove independence?
Okay, do one more.
Yeah.
Do you think also this problem seems like does it have any connection to synthetic data generation?
In a sense, yes. Like if you have a well-defined, let's say, understanding of what your, like, let's say, if your distribution assumption initially is correct, then of course you're getting good samples. But if it's wrong, then of course not. In this, for example, on distributions over k, I think which is widely applicable. Let's say you're looking at patients who have diabetes of no diabetes type 1, type 2. So you know the value of k is 3. And then this will work for any distribution, no matter what. So I think it definitely has applications in synthetic data generation. Yeah.
Okay, thank you.
Other questions?
Hey, thanks for the great talk. Can you tell for the strong case, why do you have m squared? I didn't follow that.
This comes from the fact that, there was this baseline technique which I mentioned. Let me go back. So there is this baseline technique, right?
Yeah.
Basically what you have is, like, if you have a weak multisampler with sample complexity n of alpha, then you have a strong multisampler with sample complexity alpha over m. So now if you replace alpha with an alpha over m, so that gives you an additional factor of m in the sample complexity. That's why the m becomes m squared.
It's like uses tensorization.
Yeah, it's very simple tensorization, that's all.
Any other questions? I'll ask one quickly, I guess. Yeah, you guys introduced this new algorithm for like the even m equals 1 case, which is kind of cute. Do you think that's necessary, or do you think like the previous techniques could have been used for multi-sampling in a similar efficient way, or was it really dependent on your technique?
So I think the old ideas will not work because we are very much looking at this concept of this local randomizer, which is this k-array randomized response that I talked about. And this has a very cool property, is like it also somehow is working for the m equal to 1 case with subsampling, but if you allow shuffling, it somehow also works for the general m case. Now for other classes of distributions, we haven't been able to find a good local randomizer, but we hope that there might be also a research direction there, like develop better local randomizers for other classes of distributions.
Gotcha. Okay, let's thank